In this section, I'll be discussing carbon dioxide equilibrium. Now what you can see here is a molecular model of carbon dioxide. In the middle there, the black ball is representing carbon. Carbon's always black in these models. And those two red balls are representing oxygen. And as you can see, they're double bonds. So, carbon dioxide is slightly soluble in water and it establishes equilibrium between gaseous and dissolved CO2. And the equation is there. So CO2 gas in equilibrium, and we need to remember that the symbol for equilibrium looks like that with an arrow forward and an arrow backward, going to CO2 aqueous, which is dissolved in solution. So the dissolved CO2 reacts with water to form a weakly acidic solution of carbonic acid. And we have the equation there. So CO2 gas in liquid water is in equilibrium with carbonic acid, H2CO3. You could also name this compound hydrogencarbonate. So in a closed system, such as in a bottle of soft drink, CO2 aqueous is in equilibrium with CO2 gas, which in turn is also in equilibrium with hydrogen carbonate or carbonic acid. So there's a few different equilibria going on in the one vessel, such as a soft drink. So the carbonic acid establishes equilibria involving the hydrogen carbonate and carbonate ions. So here we have another equilibria altogether, and they're all going on at the same time. So our equations for this is hydrogen carbonate or carbonic acid going to a proton and a hydrogen carbonate ion. The other equilibria is the hydrogen carbonate ion going to a proton and a carbonate ion. And you can see that they have a different valence there, -1, and this one's -2. So this one has lost 1 proton, and this ion has lost 2 protons from the hydrogen carbonate molecule. So, just to remind you of the equation at the top, if we change the pressure, temperature, or concentration of any of these substances, we can alter the equilibrium position of the system. So this all goes back to Le Chatelier's principle. Now, looking at those 3 different condition changes, if the concentration of CO2 gas is increased, the equilibrium shifts to the right to use up the added CO2. So looking at the equation, if CO2 gas is increased, the equilibrium will shift to the right to compensate for this change. So I'll just go through a couple of different examples. Okay, if more carbonic acid is added to the system, the equilibrium will shift to the left. So if we have a look, if we increase the concentration of this species, the equilibrium will want to shift to the left to compensate. So if H2CO3 is removed, the equilibrium will shift to the right to make more of it. Okay, so concentration changes are quite sort of easy to predict where the equilibrium will lie. It just basically, the equilibrium wants to go in the opposite way of what the condition change is going to be. So now looking at changing the pressure. This will also alter the equilibrium position because a gas is present. Okay, so if you had an equation or a reaction that had no gases present, then changing the pressure would have no impact on the equilibrium change. So when you see equations that have gases present, think that, and it's in equilibrium, think that the pressure, a change in pressure, will have an effect on that equilibrium. So with increasing pressure, the equilibrium will move to reduce the pressure. So it has to do with the number of molecules that are present. The equilibrium here will move to the right because there are less molecules. If you have a look at the equation, you can see there's 2 different molecules on the left and there's only 1 on the right. So the equilibrium will move to the right. Again, changing of conditions, looking at temperature now. Changing temperature will also alter this equilibrium. And this reaction is actually exothermic, so heat is given off. So we could rewrite it, CO2 gas plus water going to hydrogen carbonate and heat. So let's look at a temperature change and how that affects the equilibrium. If we heat the solution, it'll make the equilibrium move to disperse this heat. So it will want to get rid of that heat. So what will happen? Less CO2 will dissolve because the solution becomes warmer. Equilibrium will shift to the left because it's trying to get rid of that heat, to disperse it by going back to the product side of the reaction. So it will actually produce more CO2 gas, so therefore less carbon dioxide will actually be dissolved in the solution. Okay, so remembering back to our first equation, CO2 gas in equilibrium with CO2 aqueous, that's what we have to consider when we're thinking about quite a complex number of things that are actually occurring, because there are so many equilibria in these types of reactions. So this explains why gases are less soluble in warm water than in cold water. It has to do with the movement of equilibria and Le Chatelier's principle. So that wraps up the theory part for this section. So let's look at a few questions now. Okay, question 1. Describe the solubility of carbon dioxide in water as an equilibrium reaction. So, carbon dioxide is soluble in water, and its solubility increases as the temperature decreases. So, let's look at the equation, and always keep these equations in mind when you're thinking about which way will the equilibria lie. So, when carbon dioxide dissolves in water in a closed system, like a soft drink can, as I mentioned earlier, the following equilibrium can occur. So describe the solubility. It is soluble in water. And write the reaction. So remember this reaction, CO2 gas with water going to carbonic acid. Question 2. Why do soft drinks go flat when taken out of the fridge? Now, as the drink warms up, the dissolved carbon dioxide will come out of the solution because it's becoming less soluble at higher temperatures. And this has to do with the equilibrium and the changing of conditions. If you remember back, concentration changes, volume changes, pressure changes, and concentration changes, I think I just said, will all affect the equilibrium. So, carbon dioxide bubbling out of solution causes the fizz. So with less carbon dioxide, the drink will go flat. So you can try this at home actually, if you get a can of soft drink and leave it out and in the sun and get it nice and warm, and put one in the fridge and have two side by side. If you open both of them at the same time, you'll find that the warmer one will have less fizz. Question 3. Dentists are concerned about increases in dental corrosion of teeth caused by an increase in the consumption of soft drinks, including diet drinks and sports drinks. The corrosion occurs because. Now we've got a number of options here, so let's think them through. Part A. Soft drinks have a high calorie content. Okay, that may be true, but a high calorie content really has nothing to do with teeth corrosion and enamel breakdown, so we can rule that one out. Part B. Carbon dioxide kills the bacteria which cause teeth to decay. Now, some bacteria can cause your teeth to decay. That's one of the reasons your teeth can decay. But carbon dioxide wouldn't kill enough bacteria to have any effect on that. So B would be wrong. C, sugars in the soft drinks erode teeth enamel. That's incorrect because the sugars actually feed the bacteria which decay your teeth, but it's not the actual sugars that are decaying your teeth. So if we look at part D, hopefully this is the one. Carbon dioxide dissolves in water to form an acid. We know that's correct. And acids are corrosive. We also should know that that's correct because we know that we have to be very careful with acids. So our answer to this question will be part D. It's the acids that are produced by carbon dioxide dissolving in water and in your saliva. So that's the final question for this section.